So thanks again for having me here. And what I would like to talk about now is just the opposite. So I'm going to the lower metallicity range. And in particular, I would like to talk about the origin of Travel Star, HE1327, which many people before us have been trying to understand, because it's quite a special star, as we will see. So this is a bit of what I want to talk about. First, an overview of this star, a summary of first stars, the interpretation of travel stars, so this descendant of a massive star, whether low and intermediate mass stars might play a role in their origin, and we believe so. And then I'll draw the main conclusions. So Travel star HE1327 was first detected by Anna Frebel in 2005. It wasn't sure whether it was a main sequence or a subgiant star. New Gaia measurements seem to point to the fact that it's probably a subgiant. There's no evidence of binarity, but after all, it's been only about 19 years that it's been discovered. So still it could be a long period binary. It's located in the halo, so go away from the butt and go to the halo. It's low mass, so 0.8 solar masses, and its metallicity is somewhere but minus 5.2. It increased in the last work, in 2018, but it's somewhere between minus 5.2 and minus 5.8. It's CNO rich, actually, very enriched, highly enriched in carbon, nitrogen, and oxygen, especially so in nitrogen, and also, and this is important, it's enriched in strontium and barium. Why is this star so special? Well, actually, there are only 14 stars with metallicity lower than minus 4.5, and our star is below minus 5. So it's probably the descendant, it's one of the first generations of stars. It's probably the descendant of the real first stars, or perhaps the granddaughter of the real first stars. These first stars forms in dark matter mini halos of about 1 million solar masses, and just a few hundred thousand years after the Big Bang. They sparsely polluted the interstellar medium, and after them, the second star generation was born, and of course it kept the nucleosynthetic signature of these first stars. So it would definitely be very exciting to be able to detect second generation stars, because they would give us a lot of information about how the first stars were. And of course, it would be even more exciting to find a real first generation star. But is that possible at all? Well, it depends on the initial mass function. The first simulations of formation of metal-free stars, of real primordial stars, pointed that only massive, or actually very massive stars could form. But later simulations with more physics in it and higher resolution point to the fact that actually low and intermediate mass stars might form at zero metallicity. So this is very interesting, but still the main working hypothesis is that probably first stars were only massive stars. Okay, if we think of our star as a Frebel star, as a single star, it could be it could have been born in an intermediate interstellar medium polluted only by a massive star, or perhaps by a massive and a low or intermediate mass star. If it is a binary, a long period binary, so we have not information about its companion, but if this is a binary, it could have been the low mass companion of a star that went through the AGB, and these travel stars, this low mass companion, at some point accreted by enhanced wind accretion, accreted matter synthesized during the AGB. And what we can see now in travel star is a pure envelope produced by AGB material. So in the line of what Julia was talking about. Of course, second generation stars could form from massive binaries, but we will not care about those here. As you may guess, because the main working hypothesis points to the fact that primordial stars were massive, this first scenario would be the most popular. This is what we are going to see in a while. Okay, a bit more details about the composition of travel stars. This is a rather recent update, but the main features are quite similar to what it was found in 2005. So heaps, so more than 1,000, almost 10,000 times more carbon, nitrogen, and oxygen compared to iron than in the sun, especially a lot of nitrogen. So you will always have this pattern, carbon, nitrogen, oxygen versus iron. Very huge. Then what we call the light element slide, sodium, magnesium, and aluminum, very high and decreasing. And then let's look down there, the presence of strontium, 10 times more compared to iron than in the sun. So very quickly after its discovery, there was this interpretation of what the origin of travel star was. And the first attempt was by Iwamoto, 2005, and they assumed that it was probably the daughter of a mixing and fallback supernova. So again, let's think of what Julia said about, and she mentioned that very metal stars tend to want to collapse to form black holes. These stars are sort of halfway because there's a part of their inner regions that they get mixed, and then the innermost part of this mixing and fallback supernova collapse to a black hole. So of course, whatever is collapsing to a black hole will not be ejected to the interstellar medium. The thing with these models is that models have lots of parameters to play with. So of course, the initial mass of the star, the initial metallicity, but the limits, the boundaries of these mixing regions change. So you can get anything from iron peak elements, silicon, neon, anything there. So these mass limits can change. Of course, the mass limit for the formation of the black hole may change. The energy of the explosion changes and changes the nucleosynthesis. So altogether, there's many parameters. So, and of course, you can get very different results. However, even if you play with all these parameters, Ezedin et al. In 2019 showed that the best you can do to fit the abundance of travel star is 82% of the elements, even playing with all these parameters. They struggled certainly to get enough nitrogen. That's very typical of supernova models, and they struggled to get the zinc, as you can see. So what was the option? Yet another type of supernova, and what's called an spherical supernova explosion. So with this, they can play with modified densities, and they can choose the different at different latitudes of the star. These mass limits for the fallback and the mixing can change, can be altered, and in this sense, they succeed to reproduce the zinc. Still problems with the nitrogen, but it is a rather successful fit. Is it? But you might remember that something's missing. Remember the strontium? These supernova models cannot produce strontium. So there's the hypothesis that if rotation is implemented in these models, in supernova models, we might get S-process elements. However, at this moment, there's no successful model reproducing S-process elements in this and fitting travel star. It's not only a strontium, but also Molaro et al. Last year found that this star is highly enriched in barium as well compared to iron. So again, more than 10 times. Still, this travel star is still called a CEMP no. So it's in all the literature, you read that it's a SMNO, that is, it has no S-process enrichment. But you see, it's probably not very accurate to describe it like that. So what's the idea? Which are the typical sources of S-process? Julia also talked about this. She did a lot of work for me, so thank you. Of course, intermediate mass stars, low and intermediate mass stars. So let's go back to these alternative scenarios. And actually, this is a null hypothesis. Simon Campbell, in his PhD thesis, already showed that with hypermetal poor stars, you could get this interesting carbon, nitrogen, oxygen pattern. The light element slide, and Simon with Amanda Caracas and Maria Lugaro, they worked out the detailed nucleophase synthesis of a one solar mass star, which went through a proton ingestion episode, so actually dual core flash, and they could, with their yields, they could reasonably fit carbon, nitrogen, and oxygen, and strontium, well, within a factor of 4, but they overproduced barium. Also, Cruz et al. In 2013 also tried to match the yields of a one solar mass star, again, of different extremely metal poor values. They tried to match the composition of travel star, but they couldn't simultaneously get the light elements and the heavy elements. So it was a problem. What we have done is try with a 3 solar mass star. We did a work in 2022 where we could see that a 3 solar mass of a composition similar to the one of initial composition similar to the one of travel star, we could reproduce the carbon, nitrogen, oxygen peak, the light elements light. So it was very promising. So we went through the nuclear synthesis with different carbon-13 pockets, and we compared our results to travel star. I will show that later. So anyway, we could get the CNO that we wanted, carbon and oxygen, especially carbon, very little oxygen from the third recap, nitrogen for the second recap, and then hot bottom burning, which appears somewhere in the advanced TPH evolution, not from the beginning, but it does appear. We also could get the correct nucleosynthesis to get the light element slides. So the combination of helium burning, proton captures in the hydrogen burning shell, and then third recap. And of course, we could get the S-process elements and be dredged up to the surface. So this is what we get up here in golden. So it's quite a nice match. Well, we have the problem of oxygen, and indeed, we have the problem of zinc. But barium and strontium are nicely fitted. The light element slide is reasonable, and the rest of the elements are very good. Just to compare, these were the results by Yezzedin. So they didn't get any S-process, and they had the problems of nitrogen. So just to compare the two results here, it's important to realize that we don't compare directly our yields. So what we have to do, of course, is dilute the yields of our stars in matter, either primordial or previously enriched by supernova. But anyway, the results are pretty good. And actually, what we're missing is what is produced with this spherical supernova explosion of the 25 solar masses. And what we are missing is what we have. So the logical idea was to combine the two models. So this is quite a preliminary result, but it's still promising because we can reasonably match a lot of elements better than the models separate. We have some problems. We overproduce some of the light elements light, but the pattern is there. The pattern is very promising. In this model, in this fit, it's important to realize that we strongly dilute the supernova ejecta, and that makes a lot of sense because when the supernova explodes, its matter goes much further than what you get from HGB winds. So a little of supernova and our yields diluted in primordial matter gets a nice fit, seems to get a nice fit to a Frebel star. And here are my conclusions. So first of all, in the literature, Frebel star is always named, it's always supposed to be a CEMP node, a sub-node star. Strontium and barium are always forgotten, but they are there and they are important. At the moment, no supernova model can perfectly explain the heavy element enrichment. So what we found is that burst formation scenario probably involves the yields from a very diluted massive star leading to a supernova and an intermediate massive star. The point, it's not only important for this Frebel star, it's only a few of them. So whenever we find a match, we want to draw many conclusions. So one of the things that this result suggests is that intermediate massive stars were there and were contributing very early in the primitive universe. And that's something that we found very interesting. So that was my talk. Thank you very much. If you have any questions.
Thanks, Amanda, go ahead. Thank you. Thanks, Pilar. Nice talk. I'm just curious about, have you compared this star to the yields or abundances from Kiefi and Lamongi's rotating massive stars? Because they produce nitrogen and S-process elements.
Yes, but they didn't work. That's one of the things. So the things that I tried, and also they didn't get the zinc.
So you have tried it.
Yes.
With this. Okay.
Yes.
It'd be nice to show that, actually, the comparison.
Yeah,
that's one question.
I did just some preliminary plots because it's, well, once you see it doesn't work, you just. But the main problem also was the zinc. It's not easy to get. Many supernovas don't provide enough zinc, and this one has a lot. It's 0.8.
Okay, thank you.
Thank you. And the other, sorry, can I extend a bit? Because I wanted to talk about this, mention this quickly, and I forgot, but you reminded me. The other interesting option would be to think, and that's interesting and exciting in many ways, to think of considering the yields of electron capture supernovas that also were mentioned by Julia, because these produce quite a lot, we haven't tried yet, produce quite a lot of oxygen and quite a lot of zinc. And it's funny, it's interesting with them, because they are the lowest mass supernovas, at least from single objects. So it's sort of hinting and supporting the fact that the primitive initial mass function was not as highly biased as it's generally believed. So we find that trying that can be very exciting as well.
Okay. Any other questions?
Hello. I'm not an expert on the field, but I have a curiosity. Do these yields of the AGB star depend on the age, on the specific age of the AGB? I mean, there is some time dependence on these results, depending on whether.
If we stop, you mean if we cut the evolution at different parts of the.
Yeah, as far as I understand, this is bring by the convective processes from inside. So there is some kind of dependence on which exact moment you stop or you take the yields.
What we're doing now is getting the yields from the entire evolution.
Okay.
So it would if we think of in terms of the scenarios. Sorry. So it would be perfect. It's more or less this. If we're thinking of a binary scenario, we would think of a pretty advanced AGB star. But however, the duration of the evolution is related to the wind recipes. That also was mentioned some moment in the questions before. The wind rates recipes are not very clear at normal metallicity stars and are just any crazy guesses almost in these extremely hypermetal metal pole stars. So what I mean is if we considered lower mass loss rates, we could interpret, we would get some similar yields at, say, halfway of the AGV evolution, before the end of the evolution. So this scenario could be matched as well, in that sense. Thanks. Yes, I wanted to speak things quickly and give the general message, and I didn't give many details, but I guess that's what questions are for.
I think we have time for one more question, if anyone in the room or on Zoom.
Thanks, Pilar, for the nice presentation. So can you specify which are the main problems of the, let's say, the free solar mass model alone to reproduce, besides the oxygen?
Hi. So that's it. Yes, we always struggle. I have asthma, so it's this oxygen issue is always a thing with me. And yes, oxygen is, we don't get enough oxygen. And then the zinc, the zinc, that this also was our barium, we don't get any zinc. They do with this spherical. But even with supernovas, zinc is not so easy to get. So it's the oxygen and the zinc. And yeah, well, oxygen is easy with supernovas, but the big success of the model, this spherical model, was precisely the zinc. That's what they struggled to get.